Most of our universe is made of something we cannot see. This is not a metaphor, but a concrete fact at the heart of modern cosmology. For nearly a century, astronomers have known that galaxies and clusters of galaxies are held together by the gravitational pull of far more mass than we can account for with stars, planets, and gas. This missing mass is what we call dark matter. It is the invisible skeleton of the cosmos, and its true nature remains one of the greatest unsolved puzzles in all of science. By the end of this investigation, you will understand the leading and most compelling theories for what this mysterious substance might actually be. We will journey from the gravitational clues that betray its presence to the exotic particles and radical ideas where it could be hiding. What do you think is the most surprising place we might find the answer? Our story begins not with a telescope's gaze, but with a simple question: how do galaxies spin? In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of thousands of galaxies bound together by gravity. He measured how fast individual galaxies within the cluster were moving. What he found was startling. The galaxies were moving so quickly that the combined gravity of all the visible stars and gas in the cluster should not have been nearly strong enough to hold them together. According to the math, the entire cluster should have flown apart long ago. Zwicky concluded there must be some invisible form of matter, which he called dark matter, providing the extra gravitational glue. At the time, his idea was largely dismissed as too radical. But the evidence would only grow stronger decades later, with a discovery closer to home. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford turned their attention to individual spiral galaxies like our own Milky Way. They meticulously charted the orbital speeds of stars and gas clouds at different distances from a galaxy's bright, central core. According to the laws of gravity as we understand them, stars farther from the center should orbit more slowly, just as Pluto orbits our Sun much more slowly than Earth does. The gravitational pull weakens with distance, so outer objects naturally move at a more leisurely pace. But Rubin's data revealed something completely unexpected. Stars far out in the galactic suburbs were orbiting just as fast as those near the downtown core. The rotation curve, as it's called, was flat. This was a profound contradiction. For those outer stars to be whipping around at such high speeds without being flung off into intergalactic space, there had to be a tremendous amount of additional gravity holding them in place. And that gravity could only come from matter we could not see. The visible galaxy, it turned out, was just the tip of a much larger, much darker iceberg. This missing mass wasn't just a curious anomaly. It was the dominant architectural feature of the universe itself. The evidence did not stop at the edge of a single galaxy. If dark matter was real, its fingerprints would be everywhere we looked on the grandest scales. And indeed they were. Take those immense clusters of galaxies that first puzzled Fritz Zwicky. Modern observations have confirmed his wild hunch with astonishing precision. We can now measure the motions of hundreds of galaxies within a single cluster. Their speeds are so incredibly high that the collective gravity of all the visible stars, gas, and dust accounts for only about 1/10 of the force needed to keep the cluster from tearing itself apart. There is simply no way to explain those frantic orbital dances without the presence of a massive, unseen anchor. A vast halo of dark matter that cradles the entire cluster in its gravitational embrace. But perhaps the most visually stunning proof comes from a cosmic illusion predicted by Einstein himself: gravitational lensing. According to his theory of general relativity, massive objects warp the very fabric of space and time around them. Light, traveling in a straight line through this warped space, will appear to bend. Think of it like placing a heavy bowling ball on a taut trampoline. If you roll a marble across the fabric, its path will curve around the depression made by the ball. In space, a massive galaxy cluster acts like that bowling ball. When light from a far more distant galaxy travels toward us, it passes through this warped space around the cluster. The cluster's gravity bends the light's path, acting like a giant, flawed lens. From our perspective, the image of that background galaxy can be stretched, distorted, or even multiplied into multiple arcs and smears of light around the cluster's edges. This is not a simulation, it is a direct photograph of gravity in action. And by studying the precise amount of distortion in these cosmic mirages, astronomers can map the total mass of the foreground cluster, both seen and unseen. The results are always the same. The amount of mass required to create the observed lensing effect is many times greater than the mass of all the glowing material we can detect. The light itself is telling us that something massive and invisible is there, bending its journey across the cosmos. These two independent lines of evidence, the frenzied motions within clusters and the ghostly lensing of distant starlight, converge on the same inescapable conclusion. Dark matter is not an error in our observations or a misunderstanding of physics on galactic scales. It is a real, physical substance that forms the underlying framework for the largest structures in our universe. The question then becomes not if it exists, but what in the world, or rather, what outside of our world it could possibly be made of. This leads us to a crucial step in any good detective story, ruling out the usual suspects. Before we can chase the truly exotic possibilities, we must eliminate the simpler explanations. Could this missing mass simply be made of ordinary stuff that's just very hard to see? Perhaps it's vast numbers of faint stars, like failed stars called brown dwarfs, or lonely rogue planets drifting in the darkness between stars. Maybe it's enormous clouds of cold, dark gas, floating unseen throughout the galaxies. These are all forms of what physicists call baryonic matter, the same kind of stuff that makes up you, me, and every star we can see. At first glance, it seems like a perfect solution, a hidden population of ordinary objects. But the universe itself has left us clues that tell a different story. Our most powerful evidence comes from the very first moments after the Big Bang, a process called Big Bang nucleosynthesis. In those first few minutes, the entire cosmos was a searing hot fusion reactor, cooking the lightest elements, hydrogen and helium, into existence. The precise amounts of these elements that were forged are exquisitely sensitive to one thing: the total density of ordinary, baryonic matter in the early universe. By measuring the ancient abundances of hydrogen and helium we see in the oldest stars and in distant gas clouds, we can calculate with remarkable precision just how much of this normal stuff the universe contains. And the answer is clear: it is not nearly enough. All the stars, planets, gas clouds, and even every dim, cold object we can imagine can only account for about 15% of the total mass required by our gravitational observations. The remaining 85% is something else entirely, a substance that does not interact with light at all, a form of matter fundamentally different from anything we have ever touched or seen. So the mystery deepens. We have ruled out the hidden cities of dim stars and the shadowy oceans of cold gas. The culprit is not merely hiding in the dark, it is made of the dark itself. So if the answer is not ordinary matter hiding in the shadows, we must look for something truly extraordinary. For decades, the most promising lead in this cosmic investigation has been a class of particles that sound like something from science fiction, yet are grounded in the elegant mathematics of particle physics. They are known as WIMP, an acronym for weakly interacting massive particles. This hypothesis became the frontrunner for a very compelling reason: it elegantly solved two major puzzles at once. The first puzzle was our missing mass. WIMP, by their very definition, are massive. They carry significant weight, providing the necessary gravitational pull to shape galaxies and clusters. But they are also weakly interacting. This means they do not feel the electromagnetic force, so they do not absorb, reflect, or emit light, making them perfectly dark. They are essentially cosmic ghosts, passing right through ordinary matter and through each other without a trace. The second puzzle was more subtle. Physicists have a remarkably successful theory called the Standard Model, which catalogs all the known fundamental particles and forces. Yet it is incomplete. It does not, for example, explain gravity's place among the other forces. Theorists working on extensions to the Standard Model kept predicting the existence of new, heavier particles that would have existed in the fiery early universe. And here is the beautiful part. Calculations showed that if a stable, massive particle interacted only through gravity and the weak nuclear force, the very force responsible for certain types of radioactive decay, then the number of such particles surviving from the Big Bang would naturally add up to almost exactly the density of dark matter we observe today. It was a stunning coincidence, or perhaps a profound clue. The universe seemed to have left a mathematical signature pointing directly at the WIMP. This elegant convergence of cosmology and particle physics made the WIMP hypothesis not just attractive, but almost too perfect to ignore. It suggested that the answer to the largest-scale mystery in the cosmos might be found in the behavior of the very smallest things. The elegance of the WIMP hypothesis demanded proof, and that meant building traps to catch a ghost. If these particles are constantly streaming through Earth, as theory suggests, then detecting even a single one would require an experiment of exquisite sensitivity. Scientists have developed a three-pronged hunt, attacking the mystery from every conceivable angle. The first approach is the most direct, and it takes us deep underground. Laboratories like the one in Italy's Gran Sasso Mountain, or in a former gold mine in South Dakota, are buried beneath thousands of feet of solid rock. This immense natural shield blocks out the constant rain of cosmic rays and other radiation from space, creating a near-perfect quiet zone. Within these caverns, scientists have placed ultra-pure crystals of materials like germanium or xenon, chilled to incredibly low temperatures or kept in a liquid state. The idea is to wait with immense patience for the one-in-a-trillion event. They are listening for the faintest whisper of a WIMP, with just enough mass and speed, bumping into the nucleus of an atom within the detector. It would be a tiny, almost imperceptible recoil, a minuscule flash of light or a wisp of electrical charge. After decades of operation, these silent sentinels have yet to report a definitive signal. The ghost remains elusive. The second strategy takes the search out into the cosmos itself. This is indirect detection. If WIMP are their own antimatter counterparts, then wherever they gather in great density, like at the heart of our galaxy, a few might occasionally collide and annihilate each other. Such a violent meeting would transform their mass into a burst of energy, creating secondary particles we can see, like gamma rays, the most powerful form of light, or unusual cosmic rays. Telescopes in space and on the ground are constantly scanning the galactic center, nearby dwarf galaxies, and other likely dark matter hotspots, searching for an unexplained excess of this high-energy radiation. They are looking for the faint, glowing signature of a shadowy crime scene, the aftermath of a dark matter particle destroying itself. The final frontier of the hunt is to create dark matter ourselves. This is the goal of the world's most powerful particle smasher, the Large Hadron Collider. By hurling protons together at nearly the speed of light, scientists recreate the conditions of the early universe, hoping to forge particles that have not existed naturally since the first moments after the Big Bang. The strategy here is not to see the WIMP directly, as it would zip right through the detector unseen. Instead, they look for the telltale missing energy in a collision. If two protons collide and the debris flying out does not account for all the energy that went in, that missing energy could have been carried away by an invisible, stable particle, a WIMP fleeing the scene of its own creation. For years, the collider has probed ever higher energies, and while it has discovered other marvels like the Higgs boson, the signature of dark matter remains absent. The combined silence from these three great experiments, the deep underground labs, the space telescopes, and the particle collider, has begun to cast a long shadow over the once bright promise of the WIMP. It is a silence that is forcing cosmologists to look beyond the familiar and consider possibilities that are, if anything, even stranger. This persistent silence from our most powerful detectors is creating a quiet crisis in cosmology. For decades, the WIMP was the elegant favorite, the particle that seemed to explain everything with a single, beautiful idea. But science advances not only through discovery, but through the careful, sometimes painful, process of elimination. We have now probed such a vast range of possible masses and interaction strengths for these hypothetical particles that the once spacious theoretical playground for WIMP has shrunk dramatically. The parameter space, as physicists call it, is being systematically closed off. This is not a story of failure, but of refinement. Each experiment that returns a null result is actually telling us something incredibly valuable. It is drawing a map of where the answer is not. And that map is guiding us away from the most expected hiding places, forcing a profound and necessary shift in our thinking. The elegant solution is being cornered by its own absence, and that very absence is the clue that the truth may be far more peculiar than we ever imagined. If the leading candidate for the universe's missing mass is fading into the background, then what other players are waiting in the wings? The search must broaden, venturing into realms of theory that challenge our most basic assumptions about what matter even is. The growing quiet in our underground labs has amplified the whispers of a different, far lighter contender. Enter the Axion, a hypothetical particle so ghostly and insubstantial it makes the WIMP seem almost solid by comparison. The Axion's origin story is fascinating because it wasn't born from the dark matter mystery at all. Instead, it emerged from a deep and subtle problem in the heart of particle physics itself, concerning the symmetry of the strong nuclear force that holds atomic nuclei together. Theorists realized that to preserve this perfect symmetry, a new, very light particle must exist. They named it the Axion after a brand of laundry detergent, because it was proposed to clean up a theoretical mess. What no one initially expected was that this humble cleaning agent might also be the chief architect of the cosmos. An Axion, if it exists, would be staggeringly lightweight, billions or even trillions of times less massive than an electron. Because of this, it would not behave like a single, discrete bullet of matter. Instead, quantum mechanics tells us it would act more like a wave, a coherent ripple in an invisible field that permeates all of space. Particles that exhibit this kind of wave-like, collective behavior are known as bosons, and this is the key to the Axion's dark matter potential. You would not have a few heavy WIMP drifting through a galaxy. You would have an ocean, a truly unimaginable number of these ultra-light waves, a number like 10 to the 80th power, more than all the atoms in the visible universe, could be filling every cubic inch of space. This vast quantum ocean would be cold, slow-moving, and frictionless, flowing effortlessly through stars and planets without a single splash. This is not a swarm of particles, it is a fluid, a single coherent entity with enough collective mass to bend the paths of galaxies. To grasp this, think of the air in a quiet room. You are not aware of each individual nitrogen or oxygen molecule. Instead, you perceive the air as a continuous, gentle presence. Now imagine that air had mass but offered no resistance, no wind or pressure, just a silent, weighty stillness that could nonetheless sculpt mountains over eons. That is the Axion field. Its influence would be the sum of its countless, gentle waves, creating a smooth, pervasive gravitational pull that guides the formation of cosmic structures without ever making a sound. While our most sensitive scales are still tuning themselves to feel such a feather-light touch, the possibility remains that the universe's missing mass isn't hiding in a few heavy shadows, but in a quiet, universe-filling hum. The hunt for the Axion is a dance with the invisible, a search for a whisper in a cosmic gale. If these waves fill the universe, how could we possibly hope to detect something so utterly intangible? The answer lies in a beautiful piece of theoretical magic. While Axions themselves ignore light, a very special set of conditions can coax them into revealing themselves. In the presence of an incredibly strong magnetic field, theory suggests that an Axion could very rarely transform into a single particle of light, a photon. It is a kind of alchemy, turning the substance of dark matter into something we can actually see. This predicted conversion is the cornerstone of every major action search, and it demands instruments of exquisite sensitivity. These devices are called haloscopes, and they operate on a principle utterly different from the massive underground tanks hunting for WIMP. Imagine a highly tuned radio receiver, but one designed to listen for a station that has never broadcast before. A haloscope is essentially a resonant cavity, a metal chamber whose size can be precisely adjusted. Inside this chamber, scientists generate an immensely powerful magnetic field, often using superconducting magnets. The idea is that if actions are streaming through this chamber, a tiny fraction of them will convert into microwave photons within the magnetic field. But here is the catch: the frequency or pitch of those microwave photons depends directly on the action's unknown mass. Since we do not know that mass, we do not know what frequency to listen for. So the experiment becomes a grand, meticulous scan. Scientists slowly tune the cavity, changing its resonant size step by minuscule step, listening at each setting for an anomalous, persistent hum of microwaves that stands out against the background noise of the universe. It is like searching for one specific, faint note across an entire piano without knowing which key it is. The signal they seek would be astonishingly weak, a whisper of power so small it challenges the limits of our technology. To hear it, these experiments are shielded in cryogenic systems cooled to near absolute zero, eliminating thermal noise. They use ultra-sensitive amplifiers, some based on quantum principles, that can detect the faintest possible signals. This is not a search for a collision or an annihilation, but for a gentle, continuous transformation. While no haloscope has yet heard the definitive note of the action, each new generation of these instruments expands the range of masses we have ruled out, tuning the cosmic piano and silencing more of its keys. The quiet persists, but the method itself is a testament to human ingenuity, building radios not for stations that exist, but for one that must. But what if the missing mass is not made of particles at all? There exists a possibility so stark and simple it requires no new physics, only a profound shift in when and how we look. Imagine the universe in its first chaotic second, a seething, dense soup of energy. Within that frenzy, random patches of space could have become so intensely dense that they collapsed directly under their own gravity, bypassing the need for a dying star entirely. These would be primordial black holes, cosmic fossils forged in the furnace of creation itself. They are not the stellar black holes we know, the remnants of massive stars that lived and died. Those are far too few to account for dark matter. Primordial black holes are something else entirely, a potential population of ancient, compact shadows that could have formed in vast numbers before the first star ever flickered into life. Their masses could range from the absurdly tiny, no heavier than a mountain, to the monstrously large, thousands of times the mass of our Sun. Each one would be a knot of pure gravity, a perfect dark object drifting through the cosmos, invisible except for the way it bends the space around it. If enough of them were scattered across galaxies, their combined gravitational pull could very well be the force we have been searching for. It is an elegant, almost minimalist solution, one that asks us to find the answer not in the unseen, but in the unseen remnants of the universe's violent birth. The idea transforms the dark matter mystery from a search for new particles into a cosmic treasure hunt for the oldest relics in existence. Yet, like any good theory, it must survive the scrutiny of observation, and the universe has provided us with clever ways to hunt for these ancient ghosts. One of the most powerful methods relies on a celestial alignment so precise it feels like magic, a phenomenon called gravitational microlensing. If a primordial black hole, or any compact dark object, passes directly between us and a distant star, its gravity will act as a tiny, temporary lens. For a brief period, from hours to days, the background star's light will be magnified, growing brighter before fading back to normal. It is a fleeting signature, a single blink in the vastness of the galaxy. International teams of astronomers have been conducting these microlensing surveys for decades, meticulously monitoring millions of stars in nearby galaxies like the Magellanic Clouds and in the crowded central bulge of our own Milky Way. They are searching for these characteristic brightenings, counting how many unseen objects of different masses cause them. The results have been both revealing and restrictive. They tell us that primordial black holes cannot make up all of the dark matter if they fall within a wide range of masses. For instance, if they were all about as massive as a large planet, they would have caused so many microlensing events that we would have seen them by now. That window is firmly closed. Another crucial constraint comes from the afterglow of the Big Bang itself, the cosmic microwave background. This ancient light carries an imprint of the universe's structure when it was only 380,000 years old. If a significant portion of the dark matter were in the form of relatively large primordial black holes, their gravity would have influenced the distribution of hot and cold spots in this early radiation in a specific way. The exquisite maps from satellites like Planck have studied this pattern and found no such evidence, effectively ruling out black holes in the mass range of large asteroids up to about 10 times the mass of our Sun as the dominant component of dark matter. So, where does this leave the idea? The hunt has not eliminated primordial black holes entirely. It has simply narrowed the hiding places. Two intriguing mass ranges remain theoretically possible. The first is on the lower end, black holes with masses comparable to a large asteroid or small moon. The second is on the much higher end, in the so-called intermediate mass range, from about 10 to a few thousand solar masses. These windows are still open, and they invite a fascinating question. Could the dark matter be a mix, a cosmic population of both featherweight and heavyweight primordial black holes, avoiding the constraints that rule out a single, uniform size? The search continues, not just for a single answer, but for an entire hidden archaeology of the universe's first moments. The quiet persistence of these cosmic shadows, from action waves to ancient black holes, reminds us that the simplest answer is sometimes the most overlooked. Before we chase particles born from equations, we must ask one more time: could the dark matter simply be ordinary matter that has grown old, cold, and utterly dark? This brings us back to an idea astronomers once took very seriously: the hunt for MACHO, an acronym for Massive Astrophysical Compact Halo Objects. The name itself paints a picture: massive objects made of normal stuff, hiding in the halos of galaxies. What would these be? Think of the dimmest stars that never truly ignited, the brown dwarfs, or the stellar corpses left behind after a star's fiery life, like isolated neutron stars or even black holes formed from stellar collapse. These are not exotic new particles. They are the forgotten remnants of the stellar life cycle, scattered like cosmic driftwood in the vast dark between the bright stars. For a time, they were prime suspects. If our galaxy's halo was swarming with countless failed stars and dead stellar cores, their collective gravity could certainly explain the rotation curves Vera Rubin measured. It was an appealingly straightforward solution, one that required no new physics, just a lot of very dim objects. The method to find them was the same gravitational microlensing technique used to hunt for primordial black holes. Astronomers would monitor millions of stars in a neighboring galaxy, like the Large Magellanic Cloud, waiting for a MACHO in our own galaxy's halo to pass in front of one. The unseen object's gravity would briefly magnify the background star's light, revealing its presence and allowing an estimate of its mass. After years of patient observation, the results came in. Microlensing events were detected, but not nearly enough of them. The surveys revealed that these compact baryonic objects could only account for a tiny fraction, perhaps 20% at most, of the dark matter halo surrounding our galaxy. They exist, but they are not the main story. This conclusion is powerfully reinforced by that same early universe evidence we discussed earlier, the primordial abundances of hydrogen and helium. That cosmic ledger places a firm upper limit on the total amount of normal, baryonic matter the universe can contain. All the stars, gas, planets, brown dwarfs, and stellar corpses combined cannot exceed about 15% of the total mass budget required by gravity. So while MACHO are real, and they do contribute a faint, unseen mass to the galactic outskirts, they are merely a subplot. They are the background characters in a much larger and stranger narrative. They teach us a vital lesson in cosmic detective work, sometimes eliminating the obvious, even the appealingly obvious, is the only way to clear the path for the truly revolutionary idea. With the dim glow of failed stars ruled out as the dominant answer, the darkness deepens, and our search must venture into realms where the very rules of gravity and space may be different. The persistent quiet from our detectors is a message in itself, pushing theorists to imagine ever more elusive forms of matter. One such ghostly possibility emerges not from outside our known particle family, but from a subtle extension of it. We must consider the sterile neutrino. To understand this candidate, we first need to revisit its famous and famously weird relatives, the standard neutrinos. Trillions of these particles are streaming through your body every second, born from the nuclear fires of the sun and distant cosmic explosions. They are among the lightest particles we know, and they famously interact with ordinary matter only through the weak nuclear force and gravity. They are so aloof that they can pass through light years of solid lead without a single collision. Yet, for all their ghostliness, they do interact. The sterile neutrino takes this reclusive nature to its ultimate extreme. It is a hypothetical heavier sibling that, as its name implies, is completely sterile. It feels no force at all except gravity. It does not partake in the weak force, the electromagnetic force, or even the strong nuclear force that binds atomic nuclei. It is a true island in the particle world, a solitary entity that could be everywhere and yet connect to nothing we can easily measure. This profound isolation is precisely what makes it a compelling dark matter candidate. If sterile neutrinos were produced in the hot, dense early universe, they would have decoupled from the cosmic soup almost instantly, free streaming outward as a kind of warm, relativistic fog. This warm quality is crucial. Unlike the cold, slow-moving WIMP that would clump easily to form galaxies, warm dark matter like sterile neutrinos would have too much early energy to settle into the smallest gravitational wells. This leads to a fascinating and testable prediction about the architecture of the cosmos. In a universe dominated by warm dark matter, we would expect to see fewer small, dwarf galaxies orbiting larger ones. The smallest structures would be smoothed out, as if the universe used a broader brush to paint its galactic landscape. Intriguingly, some astronomers point to the observed scarcity of small satellite galaxies around the Milky Way as a possible hint that dark matter might indeed have a warm component, a gentle warmth left over from the universe's fiery birth. But how could we ever hope to detect a particle that refuses to interact? Here, quantum mechanics offers a slender thread of hope. Theory suggests that a sterile neutrino might not be perfectly stable. On very rare occasions, it could spontaneously oscillate or transform into one of its ordinary neutrino cousins. When this happens, the process would release a tiny, specific amount of energy in the form of an X-ray photon. This means we are not searching for the sterile neutrino itself, but for the faint, monochromatic glow of its decay. Astronomers have turned their most sensitive X-ray telescopes, like the European Space Agency's XMM Newton, toward places where dark matter is thought to gather most densely: the centers of galaxies, clusters of galaxies, and even nearby dwarf galaxies. They scan the X-ray spectrum, looking for a single, unexplained emission line at a specific energy that has no other plausible source. It is the cosmic equivalent of listening for a single, pure note in a cacophonous symphony. A few tentative claims of such a line have been made over the years, sparking intense debate and follow-up observations, but a confirmed, reproducible signal remains elusive. The search for this spectral whisper continues, a testament to the idea that even the most sterile of particles might, in its quiet decay, leave a final, glowing clue to its existence. Yet the landscape of theoretical physics is far richer than any single particle. When the elegant simplicity of the WIMP begins to falter, creativity flourishes. Scientists have proposed entire zoos of exotic particles, each designed to slip through the net cast by our current experiments. Consider the SIMP, or strongly interacting massive particle. In a clever inversion of the WIMP defining trait, a SIMP interacts with itself through a new, strong force, while remaining mostly aloof from ordinary matter. This self-interaction is not a minor detail. It could solve a small but nagging puzzle in the dark matter story. Some computer simulations of galaxy formation suggest that cold, collisionless dark matter, like the classic WIMP, may form galaxies with overly dense, cuspy centers, a feature not always seen in real observations. But if dark matter particles could bump and scatter off each other, like molecules in a gas, that internal pressure would smooth out those dense cores, leading to galactic profiles that better match our telescopes. A SIMP would create its own hidden society, interacting vigorously within the dark halo but remaining a ghost to us. Detecting it would require entirely new experimental strategies, perhaps by looking for subtle disturbances in the way entire dark matter halos behave, rather than waiting for a single particle to strike a detector on Earth. Beyond SIMP lies an even broader concept, the hidden sector. This is a profound idea, that our entire universe of particles and forces might be just one facet of reality. Parallel to our own could exist a hidden sector, a complete shadow universe with its own particles and forces that do not couple to our light, our electromagnetism, or our nuclear forces. The only bridge between our world and this hidden one would be gravity, the universal language of mass. Dark matter, in this view, would simply be the ordinary matter of that other sector, forever invisible to our eyes and instruments because it speaks a different physical language. We would feel its gravitational pull, but its internal light shows and complex chemistry would be entirely separate, playing out in a cosmic theater next door to which we are permanently blind. These ideas, from self-interacting SIMP to entire hidden realms, are not wild guesses. They are structured, mathematical responses to the growing silence from our labs. They represent the scientific mind at its most inventive, exploring every possible corner of theory to explain the stubborn facts of observation. When one path is blocked by null results, the investigation does not end. It simply finds new and more intricate paths to walk. This proliferation of possibilities reveals something fundamental about our quest. The answer may not be a single missing piece, but a reflection of a reality far more layered and complex than we ever anticipated. There is one possibility that would render this entire search moot. What if we are chasing a phantom of our own making? This is the most radical proposition in the entire dark matter debate. The idea that there is no hidden substance at all. Perhaps the missing mass is not missing, but a signal that our understanding of gravity, the very force that shapes the cosmos, is incomplete when we step beyond the scale of our solar system. This is the core of modified Newtonian dynamics, or MOND. It is not a new particle, but a new law. The theory proposes a simple, yet profound, tweak to Newton's famous law of gravity. In the extremely weak gravitational fields found in the outer reaches of galaxies, where stars feel only a whisper of a pull, gravity could become slightly stronger than our standard equations predict. This tiny boost, according to MOND, would be just enough to explain why those outer stars orbit so quickly, without invoking any unseen dark matter at all. It is a beautifully minimalist idea, cutting through the complexity of particle zoos and hidden sectors with a single, elegant correction. And it has a surprising number of successes. MOND can predict the flat rotation curves of spiral galaxies with remarkable accuracy using only the distribution of their visible stars and gas. It can explain certain observed relationships in galaxy dynamics that the standard dark matter model sometimes struggles with, all without a single free parameter for an invisible halo. For some specific galactic puzzles, MOND feels like a key sliding perfectly into a lock. But does it unlock the entire universe? The challenges are significant and arise on the largest scales. The most powerful evidence for dark matter, remember, comes from places where we see gravity acting without any visible matter at all. Take the Bullet Cluster, a spectacular cosmic collision of two galaxy clusters. When these titanic structures slam together, the hot, glowing gas from each cluster, which contains most of their normal matter, was slowed and heated by friction, like two clouds of smoke colliding. But the vast majority of the mass in the clusters, mapped through gravitational lensing, sailed right through the collision unscathed, and is now located far away from the glowing gas. This is a direct observation of mass separated from light. In the standard model, this is perfectly explained. The dark matter halos, which do not interact with each other or the gas, pass through each other, while the normal gas got stuck. For MOND to explain this, it would require the invisible mass to still be present, but in a form of unseen ordinary matter, which runs directly into the tight constraints from Big Bang nucleosynthesis we discussed earlier. The theory also faces difficulties explaining the precise pattern of hot and cold spots in the cosmic microwave background, the detailed clustering of galaxies across the universe, and the formation of the very first structures after the Big Bang. These are phenomena that the standard model of cosmology, with its cold dark matter, models with stunning precision. Proponents of modified gravity are actively working on extensions to address these cosmic scale tests, creating more complex relativistic versions of the theory. Yet for now, the consensus holds that while MOND offers intriguing insights on galactic scales, it struggles to provide a complete, unified framework for all cosmological observations. This tension, however, is not a weakness of science, but its greatest strength. It forces us to hold two radically different possibilities in our minds at once: a universe filled with invisible matter, or a universe governed by a subtly different force of gravity. Both paths demand something extraordinary of us: to look beyond what we know and question the very foundations of our cosmic map. The elegance of MOND in explaining a single galaxy's rotation curve is undeniable, but the cosmos presents puzzles on a much grander stage. Its greatest challenge comes not from stillness but from violent collisions. The Bullet Cluster stands as a monumental case in point. Here, two immense clusters of galaxies have passed through one another in what is likely the most energetic event since the Big Bang. During this cosmic crash, the hot, glowing gas, the vast majority of the cluster's normal, baryonic matter, was slowed and heated by friction, creating the brilliant X-ray glow we see in the center. But when astronomers map the total mass using gravitational lensing, the story splits in two. The peak of the gravitational field, the true center of mass for the entire system, is not where the glowing gas resides. It is offset, found in two distinct regions surrounding the galaxies themselves, which pass through the collision largely unaffected. This is a direct, visual separation of mass from light. In the standard dark matter model, the explanation is straightforward. The dark matter halos, which do not interact with anything but gravity, sailed right through the collision, carrying the bulk of the mass with them. For a pure modified gravity theory like MOND, this presents a profound dilemma. If gravity is only a modification of the law based on visible matter, then the gravitational lensing should be strongest where the visible matter is most concentrated in the pile of hot gas. But it is not. The lensing map clearly shows the mass is somewhere else. To account for this, even modified gravity theories seem to require some form of unseen mass, not necessarily exotic dark matter particles, but perhaps a type of neutrino or other known particle in vast quantities. Yet this brings the theory back into conflict with those early universe constraints on the total amount of ordinary matter. It is a difficult circle to square. The Bullet Cluster is not an isolated case either. Other merging clusters with names like the Train Wreck Cluster or MAX J0025.4-1222 show similar separations. Each one acts as a natural laboratory, demonstrating that gravity can be sourced from places devoid of the light we associate with matter. For a theory that seeks to eliminate dark matter by tweaking gravity, these cosmic collisions are a persistent and powerful counterargument. They suggest that whatever is generating the gravity, it can be physically distinct from the stuff that shines. This forces even the most ardent proponents of modified gravity to introduce additional, complex elements into their models, moving them away from the elegant simplicity that made MOND so appealing in the first place. The universe, in its violent beauty, seems to insist that the missing mass is not a miscalculation, but a physical reality waiting to be understood. So the standard model of cosmology presents a compelling vision of our universe's hidden architecture. It tells us that every galaxy, including our own Milky Way, is not an isolated island of stars, but the luminous heart of something much larger and darker. Enveloping each galaxy is a vast, diffuse sphere of dark matter, a gravitational halo that extends far beyond the last visible star. This halo is not a solid shell, but a dynamic cloud, a swarm of unseen particles held together by their own gravity. Its density is greatest at the center, gently fading out into the emptiness of intergalactic space. This invisible structure is the true gravitational anchor of the galaxy. Without it, the rapid outer stars would simply fly away, and the elegant spiral arms would unravel into chaos. The dark matter halo provides the stable, deep gravitational well necessary for a galaxy to even exist in its current form. It is the cosmic frame upon which the bright tapestry of stars is woven. But its role goes far beyond mere anchoring. These halos are the primordial seeds from which all structure grew. In the early universe, slight overdensities in the dark matter, tiny ripples in this invisible sea, began to collapse under their own gravity. They drew in more dark matter, and their growing gravitational pull began to attract the ordinary baryonic matter, the hydrogen and helium gas that would eventually become stars. The dark matter halo formed first, creating a gravitational catchment basin. Then, the ordinary gas flowed into these basins, cooling, condensing, and igniting into the first brilliant points of light. In this view, the galaxies we see are not the primary structures, they are the consequence. They are the luminous ornaments hanging on an invisible Christmas tree. The shape, size, and even the rotation of a galaxy are profoundly influenced by the properties of its dark matter halo. A dense, compact halo might foster a tight, spherical elliptical galaxy, while a more extended, slowly rotating halo could allow for the graceful formation of spiral arms. This model elegantly explains why we find galaxies embedded within clusters, and clusters within superclusters. It is the dark matter, forming a cosmic web of filaments and nodes, that laid down the blueprint for the entire large-scale structure of the universe. The bright matter simply followed the roads and settled in the cities that the dark matter built. So when we look up at the night sky, we are not just seeing stars. We are glimpsing the illuminated tips of vast, shadowy mountains, whose true bulk and shape remain hidden in the dark, holding everything we see in their gentle, gravitational embrace. Yet even this elegant cosmic blueprint is not without its own internal tensions. The dark matter model makes very specific predictions about how structures should form, predictions we can test with incredibly detailed computer simulations. These simulations, which model the gravitational dance of trillions of dark matter particles across billions of years, are our digital crystal ball, showing us what a universe built on cold, collisionless dark matter should look like. And when we compare these simulated universes to our real one, we find a few subtle but persistent discrepancies. The first is known as the Core-Cusp problem. In the simulations, the dark matter halos surrounding galaxies like our Milky Way have a very specific density profile. They are predicted to have a steeply rising density toward the center, a sharp cusp of invisible matter. But observations of many dwarf galaxies, the small, faint satellites of larger galaxies, tell a different story. By studying the motions of stars within these dwarfs, astronomers can map out the gravitational pull, and therefore the distribution of the dark matter inside them. Repeatedly, They find that the dark matter halo seems to have a flatter, more homogeneous core, not a dense, peaked cusp. It is as if the very center of these dark matter clouds has been gently stirred, smoothing out the expected sharp peak. This could be a clue that dark matter is not perfectly cold and collisionless. Perhaps dark matter particles have a small ability to interact with each other, creating a kind of internal pressure that prevents them from piling up too densely in the center. This idea of self-interacting dark matter is one compelling way to resolve the tension, turning the sharp theoretical cusp into an observed soft core. The second puzzle is called the missing satellites problem. The most sophisticated simulations predict that our Milky Way's vast dark matter halo should be teeming with thousands of smaller sub-halos, gravitational clumps that are the seeds for satellite galaxies. Yet when we look around our own galactic neighborhood, we only see a few dozen small satellite galaxies. Where are the rest? The simplest answer is that most of those dark matter sub-halos never manage to attract and hold onto enough gas to form bright stars. They are there, but they are completely dark, invisible galaxies made solely of dark matter. This is a perfectly valid solution, and indeed, astronomers are actively searching for the faintest possible stellar systems that might be clinging to these dark halos. However, the number of truly dark, starless halos predicted by the simulations is still debated. Some newer simulations that better model the complex physics of star formation and supernova explosions show that these cosmic events can blow gas out of the smallest halos, effectively sterilizing them and leaving them dark. This suggests the satellites aren't missing, they are just hiding in plain sight, cloaked in an absence of light. These are not failures of the dark matter model, but rather growing pains. They are the intricate details that emerge when a powerful theory meets the messy, complex reality of the universe. They force us to refine our understanding, to ask whether dark matter is simpler or perhaps more interesting than we first assumed. Is it perfectly cold and silent? Or does it have a hidden, subtle complexity of its own? These small tensions in the cosmic blueprint are not failures, but invitations to look deeper. One compelling way to resolve them is to give dark matter a hidden social life. This is the idea of self-interacting dark matter. Imagine the classic model, where dark matter particles are like silent, aloof ghosts, passing through each other and everything else without a trace. Now, picture a slight but crucial change. What if these particles could feel a new, very short-range force that only affects their own kind? They would still ignore ordinary matter completely, remaining perfectly dark to our telescopes and detectors. But amongst themselves, in the crowded confines of a galaxy's core, they could gently bump and scatter off one another. This subtle interaction would introduce a form of internal pressure, like the molecules in a warm gas. And that pressure changes everything on a small scale. In a dense, collapsing dark matter halo, this self-interaction would act as a smoothing mechanism. Particles from the crowded outer regions would scatter inward, transferring energy and softening what would have been a sharp, dense peak at the very center into a more gradual, flatter core. It is a cosmic evening out. A gentle mixing that could explain why we observe those soft, fluffy dark matter cores in dwarf galaxies instead of the predicted steep cusps. The particles are not colliding like billiard balls, but rather engaging in a slow, gravitational dance that redistributes their energy over billions of years. This same principle offers a potential answer to the missing satellites puzzle. In the early universe, countless tiny dark matter clumps would have begun to form. But if dark matter is self-interacting, these smallest, least massive clumps would have a harder time holding onto their particles. The internal heat and pressure from particle interactions could literally puff them up, or even disrupt them entirely, preventing them from growing into the stable, dense sub-halos that simulations of perfectly collisionless dark matter predict. The result would be a universe with far fewer of the very smallest dark matter clumps, naturally aligning better with the observed count of small satellite galaxies around giants like the Milky Way. We are not eliminating dark matter halos, We are simply changing the rules of how they assemble on the smallest scales. The beauty of this idea is its testability. If dark matter interacts with itself, we should see its signature in places where dark matter is most densely packed. When two galaxy clusters collide, their immense dark matter halos are thought to pass through each other seamlessly. But if the particles can scatter, even rarely, it would create a slight drag, a detectable lag between the dark matter and the completely collisionless path predicted by the Standard Model. Astronomers are already looking for this subtle effect in the detailed lensing maps of cosmic collisions, searching for any hint of a shadowy friction within the dark sector itself. It is a reminder that the answer to the universe's largest mystery may lie not in inventing a simpler particle, but in discovering a hidden layer of complexity within the dark world we are only beginning to map. Perhaps the most ethereal candidate of all pushes the idea of wave-like dark matter to its logical extreme. This concept is known as fuzzy dark matter, and it asks us to envision a cosmos where the missing mass is not a fluid, but a mist, a coherent quantum fog so light it blurs the very notion of a particle. Imagine an action, but one that is billions of times lighter still, with a mass so minuscule it approaches the fundamental limit allowed by quantum mechanics. At this scale, the particle's quantum wavelength becomes enormous, stretching across entire parsecs of space. These are not tiny bullets of matter, they are continent-sized ripples in an invisible field. This profound shift in scale has a dramatic consequence for how structure forms in the universe. In the standard cold dark matter model, gravity pulls particles into clumps of all sizes, from the largest galaxy clusters down to the smallest subhalos. But fuzzy dark matter behaves differently. Those immense quantum waves have a natural tendency to resist being squeezed into very small volumes. It is a fundamental quantum effect, similar to how an electron in an atom cannot be pinned to a single point, but exists as a probability cloud. This inherent fuzziness creates a kind of quantum pressure that smooths out fluctuations on small scales. Think of trying to create a sharp, detailed image using only a broad, soft brush. The fine details simply get washed away. In a universe dominated by fuzzy dark matter, the smallest gravitational wells, those that would have seeded tiny dwarf galaxies or dark subhalos, would be erased before they could ever form. This provides a potential and elegant solution to the missing satellites problem. The model naturally predicts fewer of the very smallest dark matter clumps, which could explain why we don't see a vast swarm of tiny dwarf galaxies around the Milky Way. It also addresses the Core-Cusp issue, as the quantum pressure prevents the dark matter from collapsing into a sharp, dense peak at a galaxy's center, instead forming the soft, fluffy cores that observations seem to favor. The entire galactic halo would be more like a gently vibrating gel than a swarm of discrete points. Testing this idea requires looking for its unique signature in the cosmos. If fuzzy dark matter suppresses small-scale structure, its effects should be imprinted on the distribution of the very first galaxies that formed. Astronomers are now using the most powerful telescopes to peer back to the cosmic dawn, mapping the faint, early galaxies that flickered on in the universe's first billion years. They are searching for a telltale cutoff, a specific size below which primordial galaxies become remarkably scarce. Finding such a cutoff would be a powerful hint that the dark matter has a fuzzy, wave-like nature. It is a search for absence, for a missing piece of the cosmic hierarchy that would reveal the ghostly texture of the universe's dominant substance. This idea reminds us that the answer to the dark matter mystery may not lie in the realm of particle physics alone, but in the strange and counterintuitive marriage of quantum mechanics and cosmology, where the smallest rules govern the largest structures of all. This invisible framework did more than just hold galaxies together, it built them from the ground up. To understand how, we must travel back to a time before the first star ever shone, to a universe that was almost perfectly smooth, a thin, hot soup of particles and radiation. But it was not perfectly smooth. Embedded within that primordial glow were the faintest of ripples, tiny variations in density that had been imprinted by quantum fluctuations in the very first instant of the Big Bang. These ripples were the seeds of everything to come, and they existed in both the ordinary matter and the dark matter. Here is where dark matter's unique nature gave it the starring role. Because it does not interact with light, it was immune to the intense pressure of the early universe's radiation. Ordinary matter, the protons and electrons that would become gas, was constantly being buffeted and pushed apart by the blinding light of the young cosmos. It could not clump together easily, but dark matter, feeling only gravity, was free to respond to those primordial ripples immediately. Under the relentless pull of its own gravity, the slightly denser patches of dark matter began to slowly, inexorably contract. They drew in more dark matter from their surroundings, growing heavier and creating deeper gravitational wells in the fabric of space. These wells became the universe's first structures, a vast, invisible scaffold known as the cosmic web. Think of it like a three-dimensional network of mountains and valleys, entirely dark, stretching across the expanding universe. Only after hundreds of thousands of years did the universe expand and cool enough for light and matter to decouple, a moment we see as the cosmic microwave background. At that point, the ordinary matter, now a neutral gas of hydrogen and helium, was finally free to fall into the gravitational valleys that the dark matter had already carved. Picture a gentle rain beginning to fall across an unseen landscape. The water naturally flows into the lowest points, collecting in the valleys and basins. In the cosmos, that rain was the gas, and the landscape was the gravitational topography sculpted by dark matter. Where the dark matter wells were deepest, the gas pooled most densely. Within these pools, the gas could cool, fragment, and eventually collapse under its own gravity, igniting the nuclear fires of the very first stars. These first stars were not born in isolation. They formed in clusters drawn together by the deep dark matter well they all shared. That cluster, bound by its dark matter halo, was the seed of the first galaxy. So every brilliant spiral, every glowing elliptical galaxy we see today is not a spontaneous creation. It is the luminous aftermath, the ordinary matter that found its home, lit its fires, and told its stories within a house that dark matter built. The visible universe is the decoration, but the dark matter is the architecture, the silent, stable foundation that made all this beauty possible. That ancient light from the cosmic dawn holds a detailed ledger of the universe's infancy. The Planck satellite, a marvel of European engineering, spent years mapping the cosmic microwave background with unprecedented precision. Its mission was to measure the faint temperature differences across this afterglow, variations of just millionths of a degree. These are not random imperfections. They are the fossilized imprints of those primordial density ripples, the very seeds from which all structure grew. The pattern of these hot and cold spots, their sizes and distribution across the sky, is a complex code. It tells a detailed story about the composition, geometry, and fate of the entire cosmos. Decoding this pattern is a monumental task of statistical analysis and theoretical modeling. Scientists create countless simulated universes, each with a slightly different recipe, varying the amounts of ordinary matter, dark energy, and other cosmic ingredients. They then ask which simulated pattern best matches the exquisite map Planck provided. The result is the most accurate cosmic recipe we have ever possessed. And it leaves no room for ambiguity. To produce the precise pattern of peaks and valleys we observe, the universe must contain exactly about 5 times as much dark matter as ordinary matter. This dark matter must be cold, meaning it moved slowly in the early universe, allowing small structures to form. And it must be non-baryonic, meaning it is fundamentally different from the protons and neutrons that make up our world. This is not a suggestion from one line of evidence. It is the convergence of every measurement we can make from that first light. The cosmic microwave background acts as a universal auditor, checking the books of the cosmos when it was a mere 380,000 years old. Its verdict is clear and overwhelming. The majority of the universe's matter is something ancient, cold, and utterly foreign to the world of atoms and light. This data is the bedrock upon which modern cosmology stands, a silent echo from the beginning that insists we are surrounded by a mystery. The universe is not a random scattering of lights. If you could step back far enough beyond the local glitter of our galactic neighborhood, a grand pattern would emerge from the cosmic dark. Galaxies are not isolated islands, but instead gather along immense, thread-like filaments, weaving a tapestry of light across billions of light years. This is the cosmic web, and it is the single largest structure we can observe. These luminous threads intersect at dense nodes, where thousands of galaxies swarm together in massive clusters. Between the threads lie vast, nearly empty voids, deserts of space spanning hundreds of millions of light years. This breathtaking architecture is not an accident of star formation. It is a direct imprint, a fossilized record of the dark matter distribution that seeded everything. The bright galaxies are simply tracing the underlying skeleton, like fireflies caught in the branches of a giant, invisible tree. By conducting massive surveys that map the positions and distances of millions of galaxies, astronomers are performing a cosmic census. They are not just counting stars, they are charting the gravitational landscape that dark matter built. This map provides a statistical fingerprint, a set of mathematical relationships that reveal the hidden rules of the universe's construction. For instance, scientists can measure how likely it is to find two galaxies separated by a specific distance. This correlation function tells a profound story. It shows that galaxies have a strong tendency to cluster together on scales of tens of millions of light years, reflecting the size of those primordial dark matter halos that first drew them in. The precise shape of this clustering, the way the probability falls off as you look at larger and larger separations, is exquisitely sensitive to the properties of dark matter. Is it cold and slow-moving, allowing tiny structures to form first, which then merge into larger ones? That model produces a specific clustering pattern that matches the observed web with remarkable fidelity. A warmer, faster-moving dark matter would have smoothed out the smallest wrinkles in the early universe, leading to a web with fewer fine threads and a different statistical signature. The galaxy surveys act as a cosmic tuning fork, and the note they ring out most clearly is one of cold, patient dark matter. Furthermore, by measuring the sheer volume of those immense voids, the empty spaces between the filaments, cosmologists can weigh the universe. The size and emptiness of a void is governed by a tug-of-war between the expansion of space, driven by dark energy, and the gravitational pull of all the matter surrounding it, both seen and unseen. Larger, emptier voids suggest a universe with less overall gravitational pull, meaning less total matter. The observed voids are perfectly consistent with the cosmic recipe from the microwave background, about 30% matter, with dark matter making up the overwhelming majority of that. Every filament, every cluster, every silent void is a data point in this grand experiment. They collectively constrain the amount of dark matter, its temperature, and how it interacted with itself in the early cosmos. This large-scale structure is the final, majestic proof that the missing mass is not a local illusion, but the fundamental sculptor of the entire visible universe. The true power of modern astronomy lies not in a single instrument, but in a symphony of senses. We are no longer limited to watching the cosmos. We can now listen to its vibrations and feel its most elusive particles. This is the multi-messenger era, and it is transforming our hunt for dark matter from a solitary search into a coordinated investigation of reality itself. The first new sense is the ability to hear the universe. Gravitational wave observatories like LIGO and Virgo detect the ripples in spacetime produced by cataclysmic events, such as the mergers of black holes and neutron stars. While these detectors are not looking for dark matter directly, they are exquisitely sensitive probes of extreme gravity. Imagine if a primordial black hole, one of those possible dark matter candidates, were to collide with a neutron star. Such an event would create a unique gravitational wave signature, a chirp with a specific tone and duration unlike any stellar black hole merger. By listening to the cosmic cacophony, we might one day hear the distinctive sound of dark matter interacting with the visible world in a violent, unmistakable way. Furthermore, the very existence of black holes in certain mass ranges, particularly those mysterious gaps between stellar and supermassive sizes, could be revealed through these gravitational whispers, telling us if the early universe forged dark matter in the form of ancient, compact shadows. Our second new sense comes from the most ghostly of cosmic messengers, neutrinos. Gigantic observatories like Ice Cube, buried deep in the Antarctic ice, are designed to detect the rare occasions when a high-energy neutrino from deep space interacts with an atom. These neutrinos are astronomical telegrams, carrying information from the most violent environments in the universe's active galactic nuclei, gamma-ray bursts, and perhaps the annihilation or decay of dark matter itself. If dark matter particles accumulate and annihilate in the dense core of the Sun or the Earth, they could produce a flux of neutrinos with a specific energy signature. Ice Cube and other neutrino telescopes are constantly monitoring, searching for an anomalous excess of neutrinos from these directions that cannot be explained by any known astrophysical process. They are listening for the faint, neutral voice of dark matter transforming itself into something we can indirectly perceive. Finally, the next generation of telescopes will open our eyes wider than ever before. The Vera C. Rubin Observatory, with its immense mirror and gargantuan digital camera, will conduct a decade-long survey of the entire southern sky, imaging billions of galaxies and detecting billions of transient events. It will create the most detailed map of the cosmic web ever made, allowing us to see the subtle gravitational effects of dark matter with unprecedented clarity. It could detect the flicker of a distant star being microlensed by a rogue primordial black hole, or find ultra-faint dwarf galaxies that are mostly dark matter, providing crucial statistics for the missing satellites problem. Meanwhile, space-based telescopes like the James Webb and the future Nancy Grace Roman Space Telescope will peer back to the cosmic dawn, searching for those first small galaxies. Their presence, or telling absence, will put stringent constraints on models like fuzzy dark matter, revealing whether the universe's primordial dark matter was a cold swarm, a warm fog, or a quantum mist. The convergence of these tools, ears that hear space-time, sensors that catch ghostly particles, and eyes that map the sky in relentless detail, creates a net from which dark matter may find it impossible to escape. The mystery may not yield to a single brilliant insight, but to the patient, overlapping gaze of our new cosmic senses. We stand at a fascinating crossroads in our understanding of the cosmos. The evidence for something unseen shaping the universe is overwhelming, yet its true nature slips further from our grasp with each new experiment. This is not a sign of failure, but a mark of profound scientific progress. We have moved from a simple question about spinning galaxies to a rich landscape of competing possibilities, each with its own compelling narrative and its own unique challenges. The field is now defined by a healthy and necessary uncertainty, a creative tension that is the engine of all great discovery. On one path, the particle dark matter hypothesis remains immensely powerful. Its framework explains the large-scale structure of the universe, the cosmic microwave background, and the dynamics of galaxy clusters with a precision that is nothing short of breathtaking. The idea of an as-yet undetected particle, whether a WIMP, an action, or something from a hidden sector, is deeply embedded in the fabric of modern cosmology. It has guided billions of dollars in research and inspired generations of physicists. Yet, its strength is now tempered by a persistent, echoing silence. Our most sensitive detectors have found nothing. Our most powerful collider has seen no hint. This absence is a data point of its own, pushing theorists to invent ever more elusive and complex particles to stay ahead of the null results. It begs a subtle but critical question: are we refining a brilliant theory, Or are we adding epicycles to a beautiful idea that might be incomplete? This very question gives weight to the road less traveled, the path of modified gravity. Proposals like MOND offer a starkly minimalist solution, a single tweak to a fundamental law that elegantly solves galactic rotation without any invisible substance. Its successes on the scale of individual galaxies are intriguing and demand respect. Yet, this path struggles to navigate the grander cosmos, the bullet clusters and the cosmic web, without eventually invoking some form of unseen mass anyway. The tension between these two frameworks is not a weakness in our knowledge, but its greatest asset. It forces every assumption into the light. It compels us to question whether we are missing a new particle or a new principle. This pivotal moment is not about choosing a winner, but about recognizing that the universe has presented us with a clue so deep, it may require rethinking physics at its foundation. The mystery of the missing mass has become a gateway, and whatever lies beyond it will reshape our story of reality. The silence from our current detectors is not an end, but a call to build even better ears. This is the driving force behind the next generation of experiments. Machines of such staggering sensitivity, they border on the realm of the impossible. Projects like LUX Zeppelin or LZ, deep in a South Dakota mine, and its successor Zeno and NT in an Italian mountain, represent the relentless evolution of the direct detection hunt. Their principle remains the same: wait for a dark matter particle to bump into the nucleus of a xenon atom in an ultra-pure, multi-ton tank. But their scale and precision are being pushed to breathtaking new extremes. These are not just bigger versions of old experiments, they are leaps in engineering. To hear the faintest possible whisper, every source of noise must be eliminated. The xenon is purified to a level never before achieved, removing even trace amounts of radioactive elements that could mimic a dark matter signal. The detectors themselves are shielded by layers of water, steel, and ancient rock, and operated at temperatures colder than deep space. Their goal is to probe regions of parameter space for WIMP that are orders of magnitude more elusive than anything we have searched before. Interacting so weakly, they might only strike a single atom in a ton of material once a year. This is the quietest vigil in human history, and looking further ahead, the proposed Darwin experiment envisions a detector containing not just a few tons, but potentially 50 tons of liquid xenon. Such a colossal instrument would act as a final, definitive arbiter for a wide range of WIMP models. If a signal exists within the realm these machines can hear, they will find it, or they will finally close the book on the WIMP hypothesis with unshakable certainty. The Axion hunt is undergoing a similar revolution. While current haloscopes tune their cavities across a narrow range of frequencies, next-generation designs aim for broadband coverage, scanning vast swaths of possible action masses in parallel. Some propose using arrays of multiple cavities, or entirely new detection principles that exploit quantum amplification to hear the impossibly faint microwave hum of an action converting into light. The timeline for discovery, or for definitive exclusion, is now measured in decades, not centuries. Within the working lifetime of the scientists building them, these machines will deliver answers. They will either finally illuminate the dark sector with a clear, unambiguous signal, or they will force us to accept that the truth lies in a territory even more foreign than we ever dreamed. This is the cutting edge, a tangible future where the mystery of the missing mass could transition from a theoretical puzzle to a known fact of our physical world. While our deepest underground labs listen for whispers, other frontiers of discovery are preparing to shout. The search is accelerating on two parallel tracks, one focused on the impossibly small and the other on the impossibly large. In Switzerland, plans are already underway for the successor to the Large Hadron Collider, a machine of staggering ambition. This future circular collider would be over 50 miles in circumference, a ring of pure potential buried beneath the Alps. Its purpose is to push the energy frontier far beyond where we stand today, recreating conditions of the early universe with an intensity we can only dream of now. For dark matter, this represents a new kind of hope. If dark matter particles are connected to our world through forces even weaker than we've probed, or if they are part of a complex hidden sector with its own exotic physics, this machine could be the forge that creates them. The strategy remains one of missing energy, but with a sensitivity magnified by an order of magnitude. It would scan a vast new landscape of possible particle masses and interaction strengths, a territory that current colliders simply cannot reach. It is a gamble on scale, a belief that the answer to the cosmos's largest mystery might be unlocked by focusing an immense amount of energy into a vanishingly small point. This machine would not just test the remaining slivers of parameter space for known ideas like WIMP. It would open doors to theoretical possibilities we have not yet even conceived, probing the darkness by creating a more brilliant fire than ever before. Simultaneously, our view of the cosmic stage is about to expand in ways that will redefine our map of the invisible. A new generation of space telescopes is preparing for launch, with missions dedicated not to studying light, but to meticulously charting its subtle distortions. The European Space Agency's Euclid Telescope and NASA's upcoming Nancy Grace Roman Space Telescope are pioneers in this endeavor. Their primary tool is a phenomenon called weak gravitational lensing. Unlike the dramatic arcs of the bullet cluster, weak lensing is far more subtle. It does not create multiple images or giant rings. Instead, the gravity of all the dark matter along our line of sight, from individual galaxy halos to the vast filaments of the cosmic web, imperceptibly shears and stretches the shapes of billions of distant background galaxies. Each galaxy's image is distorted by only about 1%, a change invisible to the human eye. But by measuring the precise shapes and orientations of millions, even billions, of galaxies across enormous swaths of the sky, these telescopes can perform a statistical miracle. They can detect the coherent pattern in that sea of tiny distortions, a pattern that reveals the gravitational signature of all the matter, seen and unseen, between us and the edge of the observable universe. Think of it as looking through a vast, irregularly warped window at a field of distant candles. You cannot see the imperfections in the glass directly, but by carefully noting how each candle flame appears slightly stretched or tilted in a specific direction, you can reconstruct the exact shape and thickness of every ripple and flaw in the pane. Euclid and Roman will be the most precise window inspectors ever built. Their immense, high-resolution cameras will image over a third of the sky, measuring the shapes of billions of galaxies. From this colossal dataset, scientists will construct a three-dimensional mass map of the universe, the most detailed census of dark matter's distribution ever created. This map will do more than just show us where the dark matter is. It will tell us how it has evolved over cosmic time. By comparing the web's structure at different epochs, we can test the fundamental properties of dark matter itself. Does it truly behave as a cold, collisionless fluid as the standard model predicts? Or will the map reveal subtle discrepancies, hints of self-interaction, warmth, or wave-like behavior imprinted on the largest scales? Furthermore, by cross-referencing this dark matter map with the positions of visible galaxies and galaxy clusters, we will witness the intricate cosmic ballet between the dark framework and the luminous structures it hosts in unprecedented detail. These telescopes will not capture a single eureka, a moment, but they will provide the definitive dataset against which every theory of dark matter and cosmic structure formation must be tested. They are building the ultimate proving ground, where the abstract mathematics of particle physics meets the grand architecture of the cosmos. From the silent spin of galaxies to the cosmic web of light, the hunt for the missing mass has taken us on a journey through the very architecture of reality. We began with a gravitational clue, a simple mismatch between what we saw and what we felt, and that clue has unfolded into a universe of profound possibility. We have searched in the quiet of deep underground labs, tuned radios to hear the hum of a universe-filling field, and scanned the sky for the ancient shadows of primordial black holes. We have entertained particles that barely speak to our world, and questioned whether gravity itself speaks a different language on cosmic scales. Each path, from the elegant WIMP to the wave-like action, from sterile neutrinos to self-interacting halos, represents a different answer to the same fundamental question: what is the universe made of? The mystery persists, not because we have failed, but because the cosmos is richer and more subtle than we ever anticipated. This long search, marked by both brilliant theories and telling silences, is not a story of confusion. It is a process of refinement. Every null result from a detector, every precise map of the cosmic microwave background, every observation of a colliding galaxy cluster is sharpening our questions. We are not lost in the dark. We are meticulously charting its boundaries. The very act of looking for what we cannot see has forced us to understand the visible universe with astonishing precision. It has deepened our grasp of gravity, particle physics, and the epic story of cosmic evolution from the first second to the present day. We now know the cosmic recipe to a fraction of a percent, even if one of the main ingredients remains nameless. This is the hidden gift of the mystery. It compels us to look deeper, think more creatively, and build more sensitive instruments than we ever thought possible. The solution, when it finally emerges, will not merely fill a blank in a textbook. It will be a revelation. Discovering the true nature of dark matter would be a revolution on par with understanding that atoms exist or that space-time is curved. It would unlock a new chapter in physics, revealing either a fundamental particle unknown to our standard model or a radical new principle governing the force of gravity itself. It would tell us what the overwhelming majority of the universe's material actually is, transforming our place in the cosmos from observers of a luminous fringe to understanders of a vast, hidden whole. The answer is out there, waiting in the data of a next-generation telescope, in the signal of a future collider, or in the quiet persistence of a detector listening in the deepest dark. And when we find it, the universe will suddenly make a new kind of sense.